This lesson is titled Circular Motion Part 1. So this is sort of like the second main segment of the Advanced Mechanics topic, the Advanced Mechanics module of HSC Physics. So circular motion, what is circular motion? So by definition, an object in circular motion travels at constant speed, and the key word here is constant. So the same speed, and constantly changes direction. It's another key aspect of circular motion. Okay, changes direction and hence velocity too. Okay, so any object that's moving at constant speed and constantly changing direction in a circle is said to be traveling in circular motion. Now, the force which keeps an object in circular motion is called the centripetal force. And the formula to calculate centripetal force is quite straightforward, mathematically. It's simply given by F sub C, typically by convention, is equal to mv squared over r, where F sub C is the centripetal force with units of newtons, okay, because it's force. M is the mass of the object in kilograms, okay, kg I should say, N here for newtons. And V is the velocity of the object, I should say the linear or tangential velocity, okay, in meters per second. And r is the radius of circular motion in meters. This will make a lot more sense when I draw a diagram, which I'll do right now. So suppose you have an object, okay, let's say it's a ball being swung around. Okay, I suppose the ball's attached to a string, it's being swung around. Okay, looking overhead. So imagine you're looking overhead, bird's eye view, at someone swinging a ball overhead. Of mass, let's call it object of mass m, some radius r away from the center of the circle, traveling at velocity v. And I should say the centripetal force F sub c is directed towards the center of the circle. Okay, so the centripetal force basically provides the curvature to the object's circular motion. Okay, and its direction is perpendicular to the direction of the object's velocity. Okay, the velocity is motion, the movement. So V is the tangential velocity, the linear velocity. Why? Because the object is traveling. So to maintain the circular motion that it's in, it has to have velocity that's tangential, that's at a tangent to the circle, to the centripetal force being provided by the string itself, okay, the tension in the string, the force provided by the string. So here's another way of saying it. F sub C is perpendicular, let's say right perpendicular to, mathematically, to V. Okay, so to maintain this circular motion of the object of mass m, you must have a velocity that's at a right angle to the centripetal force, okay? And it makes sense. I mean, when you let go of the string, the object in this case will fly off, right, in a straight line. Okay, you can try this at home, just a string and a ball that's tied up, swing it around your head and then let it go at a point along the motion. It'll just fly off in a straight line. And that's why it's called linear velocity for V. So some examples of circular motion. So number one, that's what I talked about just now. It's a mass swung around on a rope or a string. And the centripetal force in this case is basically the tension in the rope. Okay, the force provided by the rope. Another example of circular motion is that of a car driving around a bend, or even a roundabout. And in this case, the centripetal force is provided by the kinetic frictional force between the car's tires and the road. And I should stress here kinetic because the car's moving, right? There's a frictional force, there's a kinetic frictional force that's acting on any object that's in motion. If an object is stationary, if the car's stationary, then it's the static frictional force. And number 3, a spacecraft or a satellite orbiting Earth. And the centripetal force in this case is the gravitational force from Earth. Right, so any satellite that's orbiting around Earth, it's doing so because of the gravitational pull due to the Earth. So there's some examples there. And these are typical in HSC questions, in HSC physics paper. It tends to pop up a lot. So in addition to centripetal force, there's also something called centripetal acceleration. The concept of centripetal acceleration. So as I mentioned before, an object in circular motion has changing velocity, right? Velocity is constantly changing, it's changing direction. The object is changing direction, hence its velocity is changing. And it's also accelerating too. Okay, and this acceleration, let's call it A, is directed towards the circle's center and is constant. Just like the centripetal force is constant too. Okay, this is called centripetal acceleration. And mathematically, it's a simple formula. A sub c is equal to v squared over r, where A sub c is the centripetal acceleration with units meters per second squared. V is the linear tangential velocity, units meters per second. R is the radius of the circle, which is just I should say meters per second squared, sorry, all of that squared. Radius is m. So how do we get the meters per second squared for the centripetal acceleration? It's very simple. Meters squared per second squared per meters is just meters per second squared. Okay, cancel out. The proof for this, if you want to know the proof, it's pretty straightforward. So here's the proof for the centripetal acceleration formula. So we'll start off with F equals ma. And we'll start, and F sub c is equal to mb squared over r. Okay, so the object in centripetal motion, in circular motion, is experiencing a force due to the tension of the string, right? And from F equals ma, we know that you need a force to get something moving, which in this case is the object of mass m, right? So we need to start off with these two, and we need to equate them, right? Because this is what's experienced by the moving mass. So ma is equal to mb squared over r. The m's cancel out, and so we're just left with a equals to v squared over r, the centripetal acceleration. And I should also note that in the case of circular motion, Newton's first law is relevant because an object, as you know, will continue to move in a straight line unless acted upon by external force, which in this case is the tension in the rope. So that's why the tangential, the linear velocity is directed at a right angle to the centripetal force, okay? Because the object will continue moving off in a straight line when the rope is let go of. So let's do some examples now. Example 1. So suppose you have a 1 kilogram ball attached to a 1/2 meter long string swung around in a circle traveling at velocity 6 meters per second. what's the centripetal force and what's the centripetal acceleration. So I've got to calculate these two quantities. How do we go about this? Well, the first thing we do in physics, as is the case in maths, we write down what we know first, right? So what do we know? We know what m is, mass of the ball. We know what r is, that's half a meter. And we know what v is, 6 meters per second. So let's write it down here again. We know what m is, 1 kilo. We know what r is, 0.5, half a meter. And we know what v is, 6 meters per second. That's all we know. We need to work out the centripetal force and the centripetal acceleration. So far so good. We need to also make sure we're checking the units for mass, radius, and velocity in this case. Yes, they all satisfy the SI units. So mass is kilograms, radius is meters, and velocity is meters per second. So far so good. Number 2, relevant formulae. What are the relevant formulae we need? Well, we need the formula for the centripetal force, which is just mv squared over r, and the formula for centripetal acceleration, which is just v squared over r. So let's work out, let's say, the centripetal acceleration first. It's just simpler. Start off with this formula. Okay, what's v? So v is simply 6. All right, so 6 meters per second squared. And I tell students, always write your units. Don't ever leave them out, right? And what's r? R is 0.5 meters. Okay, so the units are great as well because it's just a sanity check to make sure the units are correct at the very end of the calculation. And what you get is 72 meters per second squared. Okay, therefore, centripetal acceleration is that. Let's now work out the centripetal force. Okay, it's mv squared over r. What's m? From up here, it's 1, right? So it's 1 kilo times v squared. V squared is just 6 meters per second squared, divided by r, which is just 0.50 meters. You could also just do v squared over r in this case, because it's just, you're just multiplying everything here by 1, right? M is just 1. So you get the same answer of 72. However, it's not meters per second squared, it's newtons. So that's how you do this problem. Straightforward, just substitution. Let's do another example. Suppose you have a 5 kilogram object, a mass of 5 kilos, in circular motion. I should say with in circular, so traveling in a circular path. With radius 20 meters, with a force of 400 newtons applied. Let's work out the speed, the velocity of the object. So same as before, we need to first identify what we know. So we know what the mass of the object is. We know what the radius of the object is, of the circular path is. We know what the force being applied is. So in this case, it's the centripetal force. We need to identify that because the tension in the rope is what provides the circular motion. And we need to work out V. So M is 5 kilograms. Let's make sure we've got SI units, which we do. R is 20 meters. F sub C is 400 newtons. And V is the unknown. So what formula do we use for circular motion? Well, we use this. F sub C is equal to mv squared over r. Number 3, let's plug in what we know and what we don't know as well. So 400 newtons is equal to m, which is 5 kilograms, times v squared divided by r, which is 20 meters. This is now just a matter of algebra, rearranging the expression we have here. So let's take the 20 over here. So I've got 400 newtons times 20 meters. I'm going to do this using lots of labor because I want to make sure that everyone's following this as I'm doing it. Even if you know how to do this in like one step, make sure you just do this rigorously, step by step. In the HSC, tip for the HSC. You know, under exam conditions, you tend to get you tend to get stressed sometimes and just anxious. So it's good to just work through things step by step, just to make sure you get nothing wrong. You get this expression here, so we can now rearrange this and get V by itself. So therefore, V squared is equal to 400 newtons times 20 meters divided by 5 kilograms. So to get the V squared by itself, divide everything by 5 kilograms. So the 5's cancel here. So you get V squared is equal to 1600 Newton meters per kilogram. And then taking the square root of this expression here, you get that V is equal to 40 meters per second. Okay, and that's the answer. So centripetal circular motion is a straightforward concept using the formula mv squared over r. And you can find the centripetal acceleration as well, just using v squared over r.